Today, we're going to build an atom from the ground up, and in the process, we're going to uncover the strange, beautiful, and kind of weird reality of what everything is actually made of. Let's dive in. Okay, let's just get this out of the way. You probably have a picture in your head of an atom, right? The little solar system with electrons zipping around the nucleus like tiny planets. It's a nice, neat image, and it is almost completely, totally wrong. The reality is so much weirder. So, if we're throwing out that old solar system model, what are we replacing it with? Well, we have to start by getting rid of a very fundamental idea, the idea that an electron is in any single place at all.
Yeah, that's the big question, isn't it? It's really the central question of all of quantum mechanics. And the answer isn't a location, it's a cloud of possibilities.
This is where our brains have to take a little leap. We can't actually know where an electron is. We can only know where it's most likely to be. The math gives us something called a wave function, which is a bit weird. It can be positive or negative. But when we square that function, we get this probability density. It's a cloud, a smear of existence that shows us the regions where the electron probably is. It's not a path, it's a haze. So how on earth do we describe these fuzzy clouds of probability? Turns out there's an incredibly elegant system. Think of it less like a map and more like an address.
That's right. Every single electron in an atom has its own unique four-part address. These are what we call quantum numbers. And these four numbers tell you everything you need to know: the electron's energy, the shape of its cloud, and even which way it's oriented in space. The whole shebang.
So the first part of the address is n, the principal quantum number. This is the big picture, kind of like the country or the state you live in. A higher n just means a higher energy level, and that the electron's cloud is, on average, further away from the nucleus. Next up, we have L, the angular momentum number. So if n is the state, L is the city. This number is what defines the fundamental shape of that probability cloud. And these shapes can be simple spheres, or dumbbells, or even more complex things.
The third part of the address is ML, the magnetic quantum number. This is the street. Once we know the shape of the orbital, let's say it's a dumbbell, this number tells us how it's pointing. Is it along the x-axis, the y-axis, or the z-axis? That's what ML tells us.
And finally, we get to the House number, spins, or spin. This is an intrinsic property of the electron itself, like its charge. It can only have one of two values, which we just call spin up or spin down. It's the final piece that makes every electron's address totally, completely unique.
So there you have it, the four quantum numbers, N, L, ML, and MS. They all work together to form a complete address, pinpointing the unique state of any electron in an atom: state, city, street, and house number. Okay, we've been talking about these numbers in the abstract. Now let's see how this all builds into something we can actually visualize. How does pure math turn into the actual shapes that make up matter?
This slide just illustrates that connection perfectly. The graph on the left, that's a mathematical plot showing the probability of finding an electron at a certain distance from the nucleus. But when you take that function and you map it in 3 dimensions, you get the tangible shape on the right. Math literally becomes form.
And the simplest shape you can get is the s orbital. It's just a perfect sphere. For any given energy level, there's always one of these simple spherical clouds where an electron might be found. Things get more complex pretty quickly with the p orbitals. These look like dumbbells. And remember that magnetic quantum number, ML, our street address? Well, for this shape, it can have 3 different values. So you get 3 p orbitals, each one oriented perfectly along the x, y, and z axes.
And as we go higher in energy, we get to the d orbitals, and the shapes just become even more complex and beautiful. You start seeing things that look like 4-leaf clovers, and even a dumbbell with a donut around the middle. These aren't just abstract drawings, These are the fundamental shapes that decide how atoms bond together to make molecules, and, well, everything.
So we have the blueprints for all the possible orbitals, but how do electrons decide which ones to live in? It turns out there are 3 pretty simple rules that govern everything.
First up is the Aufbau principle, which is just German for building up. And the idea is simple. Electrons are lazy. They will always occupy the lowest energy orbital available before moving up to a higher one. You always start at the bottom and build your way up. Second, we have the Pauli exclusion principle. This is a big one. No 2 electrons in the exact same atom can have the exact same address. It's just not allowed. So what does that mean in practice?
It means if two electrons are in the same orbital, sharing the same n, l, and ml values, their spins have to be opposite, one up, one down. And that's why each orbital can only hold a maximum of 2 electrons. And third is Hund's rule. The best way to think about this one is to imagine getting on a bus. People always take an empty row of seats before they sit right next to a stranger, right? Well, electrons do the same thing. When they're filling orbitals of the same energy, like those 3p orbitals, each one will take its own orbital before any of them pair up.
Okay, we have the address system, we have the orbital shapes, and now we have the rules for filling them. So let's put it all together. Let's build a real atom from scratch.
We're going to build fluorine, which has 9 electrons. So, following our rules, the first 2 electrons go into the lowest energy spot, the 1s orbital, 1 spin up, 1 down. The next 2 fill the 2s orbital, so that's 4 electrons down. We have 5 left. They go into the 3 2p orbitals. Now, Hund's rule says 1 goes into each orbital first, then we go back and pair 2 of them up. And that's it. That is the electron configuration of fluorine.
So why does all of this matter? What's the payoff? Well, because this detailed structure lets us calculate real things. Fluorine has 9 protons in its nucleus, but its outer electrons don't feel that full positive charge. Why not? Because the inner electrons create a kind of shielding effect, and using this model, we can calculate that the effective pull on one of those outer electrons is 5.2. This is the predictive power of quantum mechanics.
So from just 4 simple numbers and 3 simple rules, you get these intricate, beautiful, and sometimes downright bizarre shapes. And this isn't just a theory. This is the literal architecture of our universe. It really makes you wonder, if our simple high school picture of the atom was so wrong, what else might we be getting wrong?